sequencing will allow parents to learn all the things about their prospective children that genetics can reveal. So the genetic testing is improving, and its price is coming down. Meanwhile, stem cell research holds the promise of eliminating egg harvest. In 2007, Shinya Yamanaka, a professor at Kyoto University, and now a Nobelist, discovered how to make skin cells become like embryonic stem cells. These induced pluripotent stem cells, or iPSCs, are among today's hottest areas of biomedical research. Scientists hope to turn them into brain, heart, pancreas, and other cells that a patient's immune system will recognize as his own. Such a development would open up a world of therapeutic possibilities, but it will also transform reproduction. Eggs and sperm, collectively gametes, are also human cell types. Scientists should be able to turn iPSCs into gametes that carry a prospective parent's own genetic variations. Gametes derived from iPSCs have already been used for successful births in mice. Research is now beginning in humans. When you add cheap whole genome sequencing to stem cell-derived gametes, you get what I call easy PGD. In, let's say, 30 years, following extensive safety testing and FDA approval, a couple who want to have a baby will go to a clinic. She will provide a small skin sample. He will provide sperm. The clinic will turn her skin cells into mature eggs and then fertilize them with his sperm to make embryos. PGD today is constrained by the number of ripe eggs harvested, usually around a dozen. Easy PGD has no such limit, because the eggs are being created from tissue samples. Assume the clinic makes 100 embryos. Each embryo will then have its whole genome sequenced, and the parents will be asked what they want to know from what those genomes can tell them. Parents will be able to learn a lot from those whole genomes. First, genetic variations can confidently predict thousands of nasty early childhood diseases, each individually rare, but collectively accounting for 1 or 2% of all births. Second, genomic sequencing can predict the risk of developing many later life diseases, such as certain cancers and Alzheimer's disease. Third, parents will be able to learn something about how their future child would look: hair color, eye color, skin color, height, and more. Fourth, genetic variations provide hints about behavioral traits, like personality type or intellectual ability. Since genetic associations with non-disease behaviors are both complex and weak, this could probably only tell prospective parents whether, for example, an embryo has a 60% chance of being in the top half for some trait. Still, that's something. Finally, the tests can easily tell parents, boy or girl. After learning what they want to know, parents will then have to choose which embryos to transfer to a womb, the final step in easy PGD. But the possibilities that come from creating gametes out of skin cells go far beyond easy PGD. If we can turn skin cells into gametes, we create opportunities for people who cannot now reproduce because they do not make useful eggs or sperm, whether from disease, accident, or age. Many examples that come to mind are benign, but others seem worrisome. For example, we might make children of children too young to have useful gametes, or of people who have died but left behind carefully preserved tissue samples. This could also lead to unwitting parenthood. It is not easy to steal a man's sperm, and nearly impossible to steal a woman's eggs. But we constantly leave cells on water bottles, eating utensils, and 1,000 other places. Cells that might be made into gametes. Take yet another step. What if we could turn a man's cells into eggs and a woman's into sperm? Who would want such cross-gender gametes? Ask gay and lesbian couples who would love to have children without turning to an outside gamete donor. Today they can't. Stem cell-derived gametes do not make the ability to do this certain, but they certainly make that next step quite plausible. What would happen if a woman had a clinic make both eggs and sperm from her skin cells, create embryos for them, and then transfer one of the embryos into her womb for birth? This method risks creating lots of diseased embryos as a result of this